Well, good evening, Calc 3 class. This is a historic moment. This is the beginning of the last section of Calculus 3, but also your entire journey through the calculus sequence. And so I'm glad to be with you in this moment, and I'm excited to look at the last theorem with you. It is a great theorem to end on. So it's called the Divergence Theorem, and other places it's been called Gauss's theorem. And the Russians have sometimes called it by a Russian mathematician's name that I won't try to pronounce. I forgot his name, actually. But lots of people have looked at this and thought about it. And it says the following. So let's let E be a simple, solid region, just meaning no holes. The boundary is all sort of nice. Everything is nice, whatever that means. And let's let S be the boundary surface of E, with positive, which means outward orientation. Okay, so all we're saying here is that we want to pick nice solids, and we want S to be the boundary of the solid. So by the way, S is closed. S is a closed surface, right? Whatever it is, it's closed. And let's let F be a vector field. Again, we've seen this condition on the last several theorems whose components have continuous partials on E. So then what's true? Well, the flux of F across the surface, i.e. the surface integral of S, the surface integral of F, is equal to the triple integral over the solid E of the scalar function divergence of F. We put a dv. And so I wanted to give you a little intuition behind this result. I actually find that this one somehow makes sense to me. And so thinking about, let's just think about maybe our solid as a sphere. That was one that I could draw. So keeping in mind, we've got our vector field F, and there's vectors flying around everywhere in here. And we're thinking about F as modeling fluid flow. So then think about it with me. So the total expansion or contraction of the fluid in F, thinking about maybe adding up the expansion or contraction of the fluid in F at every point inside the solid. Well, let's just imagine that there's lots of positive divergent, meaning there's fluid flowing out of points. If there's a lot of that going on, then it's going to have to burst and push through the boundary of the solid. And so what this theorem is saying is it's saying, look, the total expansion or contraction of the fluid, that's just the divergence of the vector field. The triple integral is summing it up. It's saying take that at every point, add it up in some sense. That's going to give you the amount of the fluid passing through the surface S, and that's just exactly the flux, which is the surface integral that we talked about. So you can really see this theorem sort of playing out. If there's lots of fluid expanding out of every point, then it's got to pass through the surface. And this theorem is saying the amount of fluid passing through the surface, the flux, is the same as if you measured sort of the sum total of the divergence of F. And let's just dive in and do an example, and we'll go from there. So I wanted to look at an example with you. We're going to at least look down the path of doing this through the direct approach. So we want to find the flux, or the surface integral of this vector field F, over the unit sphere. And so I'm not going to finish the direct approach, but I wanted to set it up with you, honestly, just to give you a taste of how horrible it would be in this case. If you don't know how horrible life would be without your tool, it's hard to appreciate the value of your tool. So, okay, so the flux is the surface integral of the vector field F. And we need to parameterize our surface. Our surface is the shell of the unit sphere, so I'm going to use spherical coordinates. And, well, my rho is just 1, so I get cosine theta sine phi, cosine phi, and then I want the whole sphere, so those are the bounds on theta and phi. There's my parameterization. I've got to compute r partial theta. I won't work through the details. There it is. R partial phi, there it is. I've got to take their cross product. Oh my goodness, there it is. I simplified some of it. There's probably more you could do. And now, I already wrote awful. I wanted to say that, not show that to you ahead of time. Let's erase that. So now I get that my flux, the surface integral that I want, becomes plug the parameterization into F, dot it with R theta cross R phi, and just take a moment and feel the misery here. Can you do this problem? Yes, you can. You absolutely can. And if you really don't think you can, then you should take a Saturday afternoon and sit on your porch and drink some coffee and work it out. But it wouldn't be fun, even for me. I would not enjoy this problem. And so that's why we'll write that this is awful. And now I want to think about this problem using the divergence theorem. So this is going to be part B. The divergence theorem says that the flux of F over the surface F is the same as the triple integral over the solid bounded by S, triple integral over, I'll call it E, of the divergence of F dV. Well, I lost track of what our vector field F was. Oh, right here. Here's the divergence. And so when we take the divergence of that, we're saying partial X, partial Z, which is 0, plus partial Y of Y, which is 1. I think I said that right before. I have this feeling I might have just misspoken. Partial X of Z, which is 0. Partial Y of Y, which is 1. You're adding those 0 plus 1, and then you add partial Z of X, which is 0. So the divergence of this vector field F is just 1. And so I get the triple integral over the solid E of 1 dV. Wait a minute. We know that when you have a triple integral of 1, you're just computing the volume of E. So I'll squeeze this in. I'm going to run out of room if we're not careful here. This is equal to the volume of E. And wait a minute. This is a sphere of radius 1, and we know the volume of a sphere is 4 pi r cubed over 3. So this is just 4 pi thirds, and I'm done. I barely filled up a line for this solution versus I had just begun if we tried to do it direct. So the divergence theorem can be extraordinarily useful. So I'll break this video here, and then I wanted to work out a total of 2 more examples with you and make a comment, and then we're going to call it not only a section, not only a chapter, not only a semester, but we're going to call it the end of calculus.